All right, good morning. It's a Monday, and it's time to take a look. Oh, it's the last day of February too, isn't it? 28th. It's the last day with an F in the month name, right? And we can't do the 2/22/22 anymore. I guess we'll have to wait 11 years for 33333. Yep. You heard it here first. Okay, so what we did last week was the roguelike tutorial, but this week we're going to switch back over to crafting interpreters just to break things up a little bit. And where we left off last time with the interpreters was section 6.2, which is up here somewhere. Just need to... 6.2, the parser class. All right, so we started working on the parser. I don't think it runs yet. And we were going to handle syntax errors. Let's find out. Cargo state, oh no, git status. I guess we're all up to date. Yeah, I never pushed these changes. Okay, and then I created a couple of locks files. Bad. Oh, that was for testing or nesting. And this was just to test symbols, right? But we have this whole parser that we started building, and I don't think it's hooked in yet, right? If I say cargo run, yeah, we tokenize, but we don't parse anything. That's fine, because I don't think it's hooked up to our main. Maybe that's why I never pushed it. Yeah, so all we do is scan and then print out the tokens that we scanned, and that's it. So we're going to have to get a little more complicated if we're going to get further. All right, so let's take a look at syntax errors and see what this tells us. There we go. Come on. Okay. So a parser really has two jobs. Given a valid sequence of tokens, produce a corresponding syntax tree. And given an invalid sequence of tokens, detect any errors and tell the user about their mistakes. Don't underestimate how important the second job is. In modern IDEs and editors, the parser is constantly reparsing code, often while the user is still editing it, in order to syntax highlight and support things like autocomplete. That means it will encounter code incomplete, half-wrong states all the time. When a user doesn't realize the syntax is wrong, it's up to the parser to help guide them back to the right path. The way it reports the errors is a large part of your language's user interface. Good syntax error handling is hard. By definition, the code isn't in a well-defined state, so there's no infallible way to know what the user meant to write. The parser can't read your mind. Not yet, at least. There are a couple of hard requirements for when the parser runs into a syntax error. A parser must detect and report the error. If it doesn't detect the error and passes the resulting malformed syntax tree onto the interpreter, all manner of horrors may be summoned. Or you run into undefined behavior, right? Philosophically speaking, if an error isn't detected and the interpreter runs the code, is it really an error? I avoid crashing or hanging. Syntax errors are a fact of life, and language tools have to be robust in the face of them. Seg vaulting or getting stuck in an infinite loop isn't allowed. While the source may not be valid code, it's still valid input to the parser because users use the parser to learn what syntax is allowed. That makes sense. Okay, those are the table stakes if you want to get in the parser game at all, but you really want to raise the ante beyond that. A decent parser should be fast. Computers are thousands of times faster than they were when parser technology was first invented. The days of needing to optimize your parser so that it could get through an entire source file during a coffee break are over. but programmer expectations have risen as quickly, if not faster. They expect their editors to reparse files in milliseconds after every keystroke. Report as many distinct errors as there are. Aborting after the first error is easy to implement, but it's annoying for users if every time they fix what they think is the one error in the file, a new one appears. They want to see them all. Yeah, that's something that Rust has struggles with a little bit because there's many layers of error checking when a program is compiled. So you might fix all the syntax errors and then you say, oh, this is the last syntax error to fix, and then you run into all the borrow checker errors. Right? Those suddenly show up. So this is something that I think is one of the things that people are less than thrilled about when they encounter Rust. But once you get used to it, you learn to expect, right? So minimize cascaded errors. Once a single error is found, the parser is no longer really knows what's going on. It tries to get itself back on track and keep going, but if it gets confused, it may report a slew of ghost errors that don't indicate other real problems in the code. When the first error is fixed, those phantoms disappear because they reflect only the parser's own confusion. Cascaded errors are annoying because they can scare the user into thinking their code is in a worse state than it is. Right. So you drop a semicolon, you don't want to have the rest of you don't want thousands of errors just because one semicolon is missing. The last 2 points are intention. We want to report as many separate errors as we can, but we don't want to report ones that are merely side effects of an earlier one. The way the parser responds to an error and keeps going to look for later errors is called error recovery. This is a hot research topic in the 60s. Back then, you'd hand a stack of punch cards to the secretary and come back the next day to see if the compiler succeeded. With an iteration loop that slow, you really wanted to find every single error in your code in one pass. Today, when parsers complete before you've even finished typing, it's less of an issue. Simple, fast error recovery is fine. Okay, so panic mode error recovery. Of all the recovery techniques devised in yesteryears, the one that best stood the test of time is called, somewhat alarmingly, panic mode. As soon as the parser detects an error, it enters panic mode. It knows at least one token doesn't make sense given a current state in the middle of some stack of grammar productions. Before it can get back to parsing, it needs to get its state and the sequence of forthcoming tokens aligned such that the next token does match the rule being parsed. This process is called synchronization. Okay. To do that, we'll select some rule in the grammar that will mark a synchronization point. The parser fixes its parsing state by jumping out of any nested productions until it gets back to that rule. Then it synchronizes the token stream by discarding tokens until it reaches one that can appear at that point in the rule. Any additional real syntax errors hiding in those discarded tokens aren't reported, but it also means that any mistaken cascaded errors that are side effects of the initial error aren't falsely reported either. So, right, we err on the side of false positives rather than false negatives. That's what it sounds like, is a summation of that. The traditional place in the grammar to synchronize is between statements. We don't have those yet. That's true. Right? We have this code that generates our abstract syntax tree structures, but right now all we have are expressions. We have these 4 types of expressions: binary, grouping, literal, and unary. We don't have all the rest. Okay, we don't have those yet, so we won't actually synchronize in this chapter, but we'll get the machinery in place for later. Oh, okay, so we're going to add code to handle synchronization, but we're not going to actually use it. That's a little frustrating. I understand that why they're introducing synchronization here, but adding code that's not going to be used is just going to make Rust unhappy. I guess we'll just have to live with it. All right. Back before we went on the side trip around error recovery, we were writing the code to parse a parenthesized expression. After parsing the expression, the parser looks for the closing parentheses by calling consume. Here, finally, is that method. And I think we did a... Oh, not in this file. Parser. Yeah, I threw one in there because I wanted to see if I could get the code to compile. So yeah, we just peeked ahead and wrote this. That's fine. What we should do though is get this checked in. Right, git add source, git commit -m, section 6.2 plus the consume function from 6.3. And I'm just going to push that up, which I should have done before I ended the stream 2 Fridays ago. All right, so we wrote this. It's similar to match in that it checks to see if the next token is of the expected type. If so, it consumes the token and everything is groovy. If some other token is there, then we've hit an error. So we report it by calling this. Yeah, so we have this error. This is what we've got right now, is just generating the error from the, just by throwing it, well, returning it as a result on the error side, which I think is fine. First, that shows the error to the user by calling this. This reports an error at a given token. I don't think we actually report the error when we call error, do we? Hello? I was hoping that would jump to the error. Okay. This reports an error at the given token. It shows the token's location and the token itself. This will come in handy later since we use tokens throughout the interpreter to track locations in code. All right, let's pull up the error code. Yeah, we generate the error, but we don't report it. So let's just report it while we're here. Let error equal this guy, and then we'll just say error report, and now we can report an error. Oh, and then we have to return it. Right, this should check. Nope, supplied 0 argument. Oh, I have to supply a location. I guess we can just put quote, not toString. Yeah. Okay, after we report the error, the user knows about their mistake, but what does the parser do next? Back in error, we create and return a parse error. Okay, that's what we're doing here. An instance of the new class. Well, okay, so we generated this locks error, which contains all of that. It probably should include the token somewhere along the line, because we are generating it with a token. Oh, this is the error code. This is a special parser error. Okay, that's the difference there. Okay, so I should say fn error here. I guess we don't need the mutable self. We just need the token. And then the message, which is a string. And it's going to throw locks error. I say throw, but just return. So we're going to create a locks error. This is passing in the token itself. Here we're reporting just a line. So this is a different kind of error then. So should I put that in here? And just make this be called parse error? Maybe that's the way to do it. And we'll just include the message. So this we can return to this kind of. Oh no, we can leave this and then just create a new one here. And we'll throw the token type in there. Use create token type. This is kind of a side thing. So locks error, and the token type actually contains line number, if I remember correctly. Oh no, that's just the token type, not the line. This needs the whole token. Okay. There we go. And so we just call it token. And call this token, token.line, right? Yeah, perfect. Oh, and we're going to have to make it pub, right? And then this is going to, this is going to take an option token, because this first one is a none, right? Token none. Line is token line, and then we have message. And then I guess we go error report. And return the error. Right, now this is saying in our error reporting we should do this kind of thing here. So we can say if let sum token is equal to self token. Right, if we have a token, then we can check the token type. If token t type is equal to token type. We'll do token line at end, and then we're pushing the message right up against. Oh no, that's a report. We already wrote report before. Oh boy. Okay. My brain is breaking. I'm in report, and this is an error. This is a different error function. We have this error function and we have this error function, right? This one's in parser, which I was writing over here, and now it's gone. All right, this guy here. And this one is the general error that just reports the error, or prints an error once it gets an error back. This calls locks.error. So it's calling it on a main class, which we don't have, right? We don't have that. All we have is main. And there's no error function in here. So should we create, so I'm trying to think about how the best way to design this is should we just continue to extend this and just say report error, or just have this do a general report? We can continue this way and then just say message. Token line, right? And then else println token line at token lexeme message. Like that. Else, we don't have a token, so we're just going to print a error directly on the line. Okay, so then in parser, we're gonna create this, right? We're gonna say error, locks error, parse error, and we're gonna give it the token. And the message. And that's the whole thing. And then in consume, we're calling this error peak. Parser error. self peak message. And see if that checks. What didn't it like? Oh, I don't need to put the message here. Oh, I do. Okay, yeah. So it's like this token message. And this is also token message. Like that. Okay. Oh, this is token, some token. Oh, and if we don't have the line, what is this complaining about here about line? Oh, it's private. Didn't I change that? I did change it to pub. All right. Oh, I see why. I forgot to change this to token. Okay. And this is a private field. I guess we make them all pubs, or it would be nice if we had like accessors, or is. I'm gonna write an is pub fun is self bool, and it's just gonna return if self t type is that kind of token type. I think that would be a better way to do it. We can just say if token is t type. Oh, token is. Yeah, token is this. And we can't apply it to that. Okay. So partial EQ. And this is an unknown. Oh, this is self message. Oops, I did it twice. And this is a private field too. So how do we want to do this? Do we want also a getter for this? But Lexeme? We have display, which does the toString. I guess we could just say as string. Oh, then we have to do this. It's a moves thing. Okay. And if we do that, we're going to complain about lifetimes? No. Oh, okay. We can do that. And then in peak, we're going to have to do that. Oh, damn it. All right, so we can't save tokens because that's going to be a move, and then we have strings in there, and then token clone. Token dot. I want to have a function which just creates a new token from an existing token. I can't think of a good name for it though. Pub fun duplicate. And this, all this is going to do is say token. What's the self dot t type lexeme is going to be self.lexeme to string. Literal option object. Oh, we can't copy objects either, right? Oh. Oh, we should separate object out then into its own thing, because here's object. And I don't think we can derive clone from here, right? Because it has a string in it. Come on, L, there we go. Self, literal, clone, that's not going to work. And then the last one is line, which is going to be self line. This will allow us to duplicate a token once we fix the, yeah, we can't do this. Dupe. Move occurs because self-token type has self-token type, which does not implement the copy trait. Okay, we can fix that. Because that's just a enum. Consider borrowing. Okay. Oh, okay, so I think we did it. I didn't realize you could do this because this has a string in it. I thought it would complain that you can't do a clone on something with a string in. I'm surprised. And we can't test any of this, right? Because nothing's hooked up yet. So that's fun. So who knows if this works? All I did was keep pounding at it until it compiled. Let's take a look at what we did. So we added this option token to our error so we could store the token that caused the error. We modified the error code so that it will report as soon as we generate the error. We created this parse error, which is slightly different to a regular error in that it actually takes the token. A normal error does not have a token associated with it. And then we changed how we report it. The parser now creates a parser error with the token, and all that does is generate this. And then what else? We made line public. Maybe we'll change that back in the future. And then we created some access functions, and I call it dupe. I don't know if I can get away with calling it clone, if that would cause us issues in the future. And then that. Okay, so it compiles. We have a bunch of warnings, mostly of unused things, right? Yeah, we don't use any of this stuff. That's normal. But are there any errors that are associated function is never used? Associated function is never used. Oh, we never call parse error? Oops. Too many R's in error. Yeah, it's right here. Maybe because we never call this, which never call. So we never actually call any of these functions yet. I'm sure we're going to get there. But why isn't it complaining about all these functions not being called? Maybe because they're not public? No? I mean, it's complaining about this guy and it's complaining about this guy. All right. Anyway, so I think we're at the stage where we can move forward. This is a simple Sentinel class we use to unwind the parser. The error method returns the error instead of throwing it because we want to let the calling method inside the parser decide whether to unwind or not. Okay, so what did we do here? Yeah, so this is actually just throwing it immediately. So what does consume do? Consume does the throw. Okay, Yeah, and in Rust we don't throw anyway, so we don't have to worry about that. If we call parser error, we can just consume it at that point if we want to. Some parse errors occur in places where the parser isn't likely to get into a weird state and we don't need to synchronize. In those places, we simply report the error and keep on trucking. For example, locks limits the number of arguments you can pass to a function. If you pass too many, the parser needs to report that error, but it can and should simply keep on parsing the extra arguments instead of freaking out and going into panic mode. Hello, Dayloop. How are you? In our case, though, the syntax error is nasty enough that we want to panic and synchronize. Discarding tokens is pretty easy, but how do we synchronize the parser's own state? Another way to handle convent syntax error is with error productions. You augment the grammar with a rule that successfully matches the erroneous syntax. Parser safely parses it, but then reports it as an error instead of producing a syntax tree. Okay, this is giving an example of Unary plus. Many languages have a Unary plus. Chasing bugs and farming tomatoes. Sounds like a productive day. Okay, this lets the parser consume, right. Error productions work well because you, the parser author, know how the code is wrong. Yeah, but mature parsers tend to accumulate error productions like barnacles since they help users fix common mistakes. Yeah. Okay, I was going to say that, so we have to figure out every single possible thing that's an error. Well, no, you just add them as they become, I guess, a popular mistake to make. So synchronizing a recursive descent parser. With a recursive descent, the parser state, which rules it is in the middle of recognizing. Oh, the parser state. In other words, the rules that is currently parsing, currently recognizing, is not stored explicitly in fields. Instead, we use Java's own call stack to track what the parser is doing. Each rule in the middle of being parsed is a call frame on the stack. In order to reset that state, we need to clear out those call frames. The natural way to do that in Java is exceptions. When we want to synchronize, we throw the parser error object. Higher up in the method for the grammar rule we are synchronizing to will catch it. Since we synchronize on statement boundaries, we'll catch the exception there. After the exception is caught, the parser is in the right state. All that's left to do is synchronize the tokens. So here's the synchronize function. We're not actually going to use it according to the text that we read, I don't know, about a half hour ago. But we'll put it in here. We want to discard tokens until right at the beginning of the next statement. That boundary is pretty easy to spot. It's one of the main reasons we picked it. After a semicolon, we'll probably finish with a statement. Most statements start with a keyword, for, if, return, var, etc. When the next token is any of those, we're probably about to start a statement. I say probably because we could hit a semicolon separating clauses in a for loop. Our synchronization isn't perfect, but that's okay. We've already reported the first error precisely, so everything after that is kind of best effort. Gotcha. Okay, so we're going to write this synchronize function, which is going to take a mutable self, because we're going to call self advance. Now this is interesting because self advance, if we look at that, that just returns a token. It doesn't return an error. So we're just going to ignore it and throw away the token it advances past. While not, self is at end. If self.previous, and we just wrote this new function here, is token type semicolon, then we're going to return. And we're done. This returns void, so we don't have to worry about what's going on. And then we're going to switch peak type. Oh, so I can't use is anymore. That's a shame. Oh, and this is previous as a function call here. Like that. Right, where's previous? Let's take a look for it. There it is. Yeah, it just returns a token. Okay. So how do we match a bunch of different tokens? I mean, we use match, but we have to pull the type out. Source token. I guess we can do that this way. It kind of obviates the need for the is, but whatever. I think this is still useful. And all we're going to return is self t-type. Okay, and then we'll just do a match on self t-type. Oh, self peak token type. And we're going to say if it's token type class or fun var for if while print return. Then we're going to return. Oh, we can just use matches, right? That's what we learned last week with in the roguelike stuff we were doing. That looks kind of ugly in terms of code formatting. Maybe push that in a little bit. Let's see what cargo format does for us. And then we'll just say advance. And that advance is inside the while loop, self advance. Okay. How's that reformat? I guess it did exactly that. Okay. Let me just pull that in and see. No, I'll pull that in one more. It's not formatting it. Why? Because it's a... Something's wrong. Something's not working right. No, it doesn't format the macro. Okay. It doesn't seem to care about that either. Weird. Okay. Anyway, it discards tokens until it thinks it found a statement boundary. After catching a parse error, we'll call this and then we're hopefully back in sync. When it works well, we've discarded tokens that would likely cause cascaded errors anyway, and now we can parse the rest of the file starting at the next statement. Alas, we don't get to see this method in action since we don't have statements yet. We'll get to that in a couple of chapters. So we wrote it, but we're not going to use it. Yeah, okay. For now, if an error occurs, we'll panic and unwind all the way to the top and stop parsing. Since we can parse only a single expression anyway, that's no big loss. So now we have yet another failure in our cargo check. Okay, we're calling token type, but we're not calling token type because it's in Synchronize, which is not being called. Is this not? Oh, wait a minute. Did I forget to add this to main? Oh, that's why everything's... Okay. So let's just hit mod parser, and now we're going to get a million errors, right? All the bugs I just put in last time. Yeah, 47 errors to deal with now. This should be if matches. Okay. Expr. I don't have expr. Use crate expr. So this might take a while to get through all the errors that I introduced in the last stream and didn't realize that I introduced because I forgot to hook the compilation unit up. Locks error. Okay, that's expr, locks error, expr. Okay, so all those are just because I forgot to include that. Okay, we got from 47 to 15. That's good. Mismatch types. Oh. So this is not okay. We're just grabbing the expr. That makes more sense. And this is the same. Okay, so I made that mistake many times, didn't I? In each one of these productions. Oh no, that one should be okay, right? Because we're returning it. That one's okay. These were all returning, so maybe these are all okay. Any other place where I do that? No. Okay, down to 11 errors. Minus should be minus. Literal is a private field. And it's an option object. Oh, it's already an option. And what we're doing is wrapping it in sum. We don't need to do that if it's already an option. And what we want to probably do is clone it out, right? Otherwise it's going to say something. If I change this to pub, for example. Oh no, it didn't seem to mind that at all. Okay, good. All right, so what's the error? Mismatch types on this as well. Oh, it's expecting a token. Okay, so, but parser error only ever returns error. Maybe I should do that. I don't know if that's going to compile though. This will though. But then what's the point of having this function? I don't know. Okay, so now is match doesn't work. Oh, we don't put a ampersand there. And now this is... Okay. This is a private field, so now we say peak is t-type, because we added that function. Oh. Okay, I think we just say previous, right? And then this is also is. Yep. Expected struct token found enum option. Oh. Right, if we're peaking, we might not get... I guess we could say unwrap and just hope it doesn't panic. Oh, and now we have a problem because now we're getting a reference to it. And if I do that, it's going to complain. Nope. Something about bar checking. Yeah. Moving out of a shared reference. All right, so what's the right way to do this? Do I just return a reference and then hope that that doesn't cascade all the errors up the chain? Yeah, so this now needs to be operator.dupe. Yeah, all of these need to. Operator dupe. Okay, so in here we can take a reference, and that way we don't have to do it here. And we're still not good. So previous needs to return that, which means all of our advances need to be fixed. Dupe. And now we have an immutable borrow followed by a mutable borrow. Will that unborrow it? It does, which means now I can go and fix this to just be operator. Right? Yes. So this gets a dupe. And this gets an operator after changing all of those. Dupe. Dupe. Oops. Dupe. And then we have this one, and because that's an option. Okay, we're gonna have to figure that one out. I guess we can say unwrap, or is it okay? How do you do it? Yeah, it's or default or something. But unwrap, it didn't like unwrap. What was the reason it didn't like that? Expected enum option. Found enum token object, and if I don't do that, then what does it complain about? Oh, as ref. Okay, I can try that. Yeah, I was, oh, that's the difference here. Yeah, okay, so we just clone it. Now we have 37 warnings. So it's getting better. What are the warnings? A whole bunch of things that are never used. Oh, because we're not, yeah, okay. Fair enough, because we haven't actually, and that's, I can see here, wiring up the parser. Okay. So that's what's going to happen next. I'll actually clean up a lot of the warnings, if not all of them. Not all of them, right? Because there's a bunch of stuff we're still not doing. And then we're going to have to figure this one out. Oh, I think I just need to put a question mark there. Yeah, that fixed that one. And I think all the others are just functions are unused. Struct is never constructed. Associate function is never. Oh, and then here we're not using P, line 143. Oh, yeah, that's true. We're not. Okay, so it took us down to 35. Good. So let's commit these changes. And this is section 6.3, syntax errors. All right, so we're mostly done parsing expressions now. There's, oh, thank you, Danish Codes. Thank you for the follow. We're mostly done parsing expressions now. There's one other place where we need to add a little error handling. As the parser descends through the parsing methods for each grammar rule, it eventually hits primary. If none of the cases in there match, it means we're sitting on a token that can't start an expression. We need to handle that error too. Okay, I think we added something in there because Rust wouldn't let us compile without returning something. Yeah, so I threw this in here, but it's actually, the error should be expect expression. Like that. So that's, I think that's all that is. Yep. So with that, all that remains in the parser is to define an initial method to kick it off. That method is called, naturally enough, parse. Okay? So let's put that right at the top, right after new, pub fun parse. Self. And what's the return? Looks like it's returning an expr. Or a locks error, right? Results. And all we're going to do is return expression, and if we get a parser error, we ignore it. Okay, so then we can just return the expression, right? Option, because if we're going to return null, we want to return none. Got it. PSO22, thank you for the follow. So we're going to just call match self expression. If it's an OK, we're going to return some expr. And if it's an error, any error, we're just going to return a none. I think that's the way this gets translated into Rust. And it didn't like that. Oh, that's right. Everything has to be mutable here. And I hit F1 again. Okay, so that likes it. We got 36 error warnings now. But we're not calling parse yet. We will revisit this method later when we add statements to the language. For now, it parses a single expression and returns it. We also have some temporary code to exit out of panic mode. Just give me 1 second. That was quick. And meanwhile, Zany9, thank you. Thank you for the follow. I like your name, Zany. Okay, syntax error recovery is the parser's job, so we don't want the parser error exception to escape into the rest of the interpreter. That's fair. When a syntax error does occur, this method returns null. That's okay. The parser promises not to crash or hang on invalid syntax, but it doesn't promise to return a usable syntax tree if an error is found. As soon as the parser reports an error, had error gets set and subsequent phases are skipped. Right, that's one of the things, is that we don't have this global variable had error. We made that change. I'm not sure the best way to handle that, because when we call parse, we need to know if we should keep going. And I think just having the none should be sufficient, but let's see. Finally, we can hook up our brand new parser to the main locked class and try it out. We still don't have an interpreter, so for now we'll parse to a syntax tree and then use the AST printer class from the last chapter to display it. We still have that, right? Oh, we don't. Oh, that's right. What we did was I made it in a separate... Yeah, so maybe we should move that over. Maybe that should be the rest of the stream is getting that linked in, because we want to print it out. We want to see what it looks like, right? All right, delete the old code to print the scan tokens and replace it with this. Okay. Right now what we're doing is we're just printing out all the tokens. I'm saying delete that. So there's our scanner, and now we're going to say parser. Pass in the tokens, I guess, and then let expr is equal to parser.parse. And that could end up being a none, and if it's a none, we don't do anything, which is, you know, if expr, I guess we can just do a match here, right? Let's do it that way. And then we can, if we have to change it later, we can change it later. Match, parser parse. If it's none, return. Okay. And if it's sum, I guess we just do that, right? Because we can just have this as the end statement, sum expr, and then we're going to call AST printer. And return OK. Okay, if we're going to do that, we'll just do that, and then we'll just do that and say printer print. Do that, and then return OK. Done. And now we have to hook in AST printer. If I comment that out, it should check. Oh, parser not found in the scope. We have to include it. Use parser. Like that. Expected avec found a reference to avec. Okay, and this is saying just use to_vec. But that's just going to make a copy of it, right? And the create clone is not implemented. So should the parser take a reference? Then that would mean this would take a reference, which means then it needs a lifetime. Damn it. which means this needs a lifetime, but hopefully that's all it needs, right? Something's wrong here. Doesn't like this. Oh, it has to be mutable. Oh, okay. Oh, now we're down to 10. Sweet. Okay, but we want to hook in this AST printer, so that's not going to work. All right, so can we just copy it over? Source. Main, I guess it was called, into source AST printer. RS. Biting Bits, thank you for the follow. Okay, so this is our AST printer. We just don't need the main. But everything else should just work. Ha, he says. Let's find out. Mod AST printer. Use AST printer star. Right, and we can just do it that way. And it doesn't like it. Oh, we don't need to put the mods in here anymore, right? Oh, all these need crates? Yeah, all these need crates now because it's not main. And print is not found. Really? Oh, it's not public. Okay. Oh, right. Duh. What am I doing? This is going to be AST printer print. And let me see. Does this take? It does take itself. So we have to create an object. Let AST printer. Let's say printer AST printer. Like that. And then just say printer print. Like that. Pubstruct. All right, we're getting closer. Oh, yes. So token, we created a getter for that, right? As string. And then expert is a, what's it complaining about? Mismatched types? Oh, I just need to amp it. Okay. Amp it up a little. It still doesn't like that. Oh, as string, like this. There. Now we're down to 7. This is good. So AST printer doesn't need token type. We're not calling synchronize, that's true. This is never called? No backslash on that sucker. Yeah, it's right here. Maybe, oh, this is in synchronize, so we're never calling it. Yeah, okay. Fair enough, fair enough. All right, we just need to remove these two guys. Okay, down to 5 warnings. And we're eventually going to get to using true and... Oh, and this has a result that must be used. Okay. Boom, used. Although that's probably not going to match. Oh, it does. That's fine. I thought it might not match that. Yeah, okay, so we have just these 3 left. Perfect. So if I say cargo run, and I put this in, expected expression. I have no idea. A. 3 plus 4. It didn't complain, but it didn't print out our expression. I was about to read this. Congratulations, you've crossed the threshold, but we haven't crossed the threshold if we don't have any output. Oh, duh, because it's just, this returns a string. It doesn't actually print. What should we call this then instead of print? To string, no, let's leave it print, and then, although I don't like that name because it's not actually printing, right? Functions which are verbs should actually do the thing they say they're doing. Println, est, printer, new line, result, close that, close. Okay, cargo run. 3 plus 4. All right, so that's what we were seeing before, right? 3 plus 4 times 5. 3, let's say 4 times 5 plus 6. All right, so it's getting the operator precedence correct. Very good. Git commit. Section 6. Was it 6.4? Yeah, 6.4. Wiring up the parser and adding the AST printer. Nice. So that's pretty good. So challenges. Let's take a look at these challenges. Fire up the interpreter and type in some expressions. See how it handles precedence and associativity correctly. Not bad for less than 200 lines of code. How many lines of code is this? 892. I guess Rust is more verbose than, and we have minimal comments in this, don't we? So yeah, Rust must just be more verbose than Java. That's a surprise. In C, a block is a statement form that allows you to pack a series of statements where a single one is expected. The comma operator is an analogous syntax for expressions. A comma-separated series of expressions can be given where a single expression is expected except inside a function calls argument list. At runtime, the comma operator evaluates the left operand and discards the result. Then it evaluates and returns the right operand. Add support for comma expressions, give them the same precedence and associativity as in C, write the grammar, and then implement the necessary parsing code. That might be a little above my skill grade. I mean, it would be a matter, if we look at the parser, it would be trying to figure out where it would go in here. Because we go with expression is equality, equality is a comparison, comparison is a term is a factor is a unary, and unary is a primary. Right? So that's how it all breaks down. So the question is, where would comma go? Here. And it might go right up here, right? With expression, it says, okay, do a self-equality, and then if you see a comma, if peak comma, then do expression again. Right? Kind of like this while loop. It might be that simple. Right? What I'm saying is we say let, I'm not going to actually do it. But you say let expr is self-equality, and then while self is match comma, then we can throw away the expr and just say expr is equal to self-equality, right? And then return expr. That might be the comma operator right there. If I'm not sadly mistaken. Should we try it? Yeah, why not? Why not? So this is the old code. This is the new code. And this just becomes token type, comma. And I forgot that we need to end statements in a semicolon. Okay, let's see what happens. Cargo run. So 3 plus 4, comma 5 plus 6. Yeah, so it evaluated the first one and returned the second one. Well, it evaluated the first one and threw it away, and then returned the second one. But it didn't actually evaluate it, right? It just, like if this was an expression that the interpreter needed, yeah, so we actually need to build, so it's not that simple. It's not that simple. We actually need to build a binary expression. Something similar to a binary expression where we can evaluate each expression in turn. Because you can have multiple commas, right? You can say 3 plus 4, comma 5 plus 6, comma 7 plus 8. And they all need to be evaluated. And then the result of that whole expression is the 7 plus 8. Janktastic. Thank you for the follow. Right? I think that's what would have to happen is somewhere in our syntax tree we would have to have like a type that allows us to generate a list of expressions, like a pub struct. I can't do it here because this is generated code, but pub struct, comma expr, and it would just be pub exprs vec expr, right? And then you'd have to evaluate each one in turn. And then the result would be, the result here would be just the result of, is that the way to do it? Should we go down this path or should we continue learning crafting interpreters and then come back to these challenges later once we know more? And then it says, likewise, add support for the C-style conditional or ternary operator. And that would definitely need its own expression type. And then the third challenge is add error productions to handle each binary operator appearing without a left-hand operand. In other words, detect a binary operator appearing at the beginning of expression, report it as an error, but also parse and discard the right-hand operand with the appropriate precedence. Yeah. Huh. Okay. So we're definitely not going to do this. And we're definitely not going to do this. At least not right now. Maybe what we can do is just take a mental note and come back to the challenges later and see if we can add them all at the end. After we've forgotten everything we've learned, right? Let's say we decide to add bitwise AND and OR operators. Where should we put them in the precedence hierarchy? C, in most languages that follows in C's footsteps, place them below comparison equality operator. This is widely considered a mistake because it means common operations like testing a flag require parentheses. Yeah, this is true. Because if you do it this way, this is done first, and then it's bitwise ANDed with the flags, and that has caused any number of bugs. Should we fix this for locks and put bitwise operators higher up in the precedence table that C does? There are two strategies we can take. You almost never want to use the result from equal expression as the operand to a bitwise operator. By making bitwise bind tighter, users don't need to parenthesize as often. So if we do that and users assume the precedence is chosen logically to minimize parentheses, they're likely to infer it correctly. But for many users, it's an even faster shortcut to getting our language's ideas into their wetware using concepts they already know. Yeah, but if you make this higher precedence than this, and people are used to putting parentheses around it, it doesn't hurt, right? So I think that's fair. That would be a fair thing to do. You don't, and it wouldn't be an error. You'd still be doing the same thing. It'd just be extra brackets around it. In practice, it's often better to make the most of what users already know. Getting them to come to your language requires a big leap. The smaller you can make that chasm, the more people will be willing to cross it. Yeah, tell that to the people who wrote Haskell, right? But you can't always stick to history, or your language won't have anything new and compelling to give people a reason to jump over. All right, I think we're at, yeah, we're all clean. We just finished chapter 6. I have about 40 minutes left, 45 minutes left. So why don't we press on? If you want to properly set the mood for this chapter, so this is chapter 7, try to conjure up a thunderstorm, one of those swirling tempests that likes to yank open shutters at the climax of the story. Maybe toss in a few bolts of lightning. In this chapter, our interpreter will take breath, open its eyes, and execute some code. Ooh. A decrepit Victorian mansion is optional, but adds to the ambiance. There are all manners of ways that language implementations make a computer do what the user's source code commands. They can compile it to machine code, translate it to another high-level language, or reduce it to some bytecode format for a virtual machine to run. For our first interpreter, though, we are going to take the simplest, shortest path and execute the syntax tree itself. Right now, our parser only supports expressions, so to execute code, we will evaluate an expression and produce a value. For each kind of expression syntax we can parse, literal, operator, etc., we need a corresponding chunk of code that knows how to evaluate that tree and produce a result. That raises 2 questions. What kind of values do we produce? How do we organize those chunks of code? Here I'm using value and object pretty much interchangeably. Yeah, so we had to invent this object thing. And you know what I'm going to do? I'm going to take a moment right now and separate these out. Because they should, object should be in its own thing. We don't need token type, and we do need format. And that's all we need for object. And here we can just say use create object, right? And then delete all this. Oh, and then in main. Oh, how did this end up happening like that? So there's mod expr, mod object. I'm just going to alphabetize these because I can. Yep, and we don't need to use anything from object, so that should work. Oh, like that. And this needs object. And this needs out. Oh, this is in our generated code. Okay, source. No, it's in generate. Here we go. Generate AST mod. And this needs an object in our scanner. There we go. Okay. Yep, same issues as before. Okay, git status, git add generate and source, git commit, refactored object into its own source file. There we go. Okay, so representing values. In locks, values are created by literals, computed by expressions, and stored in variables. The user sees these as locks objects, but they are implemented in the underlying language our interpreter is written in. That means bridging the land of locks' dynamic typing and Java's static types. All right. And so far Rust hasn't given us too much of a headache using that object type. We'll see what happens as we go along here. A variable in locks can store a value of any locks type and can even store values of different types at different points in time. What Java type might we use to represent that? Given a Java variable with that static type, we must also be able to determine what kind of value it holds at runtime. When an interpreter executes a plus operator, it needs to tell if it is adding two numbers or concatenating two strings. Hello, Supercuber. How are you? Is there a Java type that can hold numbers, strings, booleans, and more? Is there one that can tell us what its runtime type is? There is. Good old Java lang object. Well, in Rust we're going to use good old pub enum object that we just invented. So that's the whole thing, right? This is emulating Java's object type in that we can store numbers and strings, and we added a nil in there, and we also have true and false for the booleans. And that actually maps right to here, right? Any locks value is object. So if we need to add more types, then we can always add more types to this. And again, I'm still confused as to why we can clone that. Given a value of static type object, we can determine if the runtime value is a number or a string or whatever using Java's built-in instance of operator. So in Rust, we're going to just use the match, right, to figure out what type it is. In other words, JVM's own object representation conveniently gives us everything we need to implement Lox's built-in types. We'll have to do a little more work later when we add Lox's notions of functions, classes, and instances, but object and the boxed primitive classes are sufficient for the types we need right now. That's cool. Another thing we need to do with values is manage their memory, and Java does that too. Oh, crap. Okay, so that's something Rust does not do. Do we need to create like an object store that we can reference? Is that going to be an issue? We have to allocate and free objects in an object store and then have references to those objects somewhere. Right now we're just cloning them everywhere and letting Rust take care of garbage collection by, well, sorry, Rust does the free on drop, right? A handy object representation and a really nice garbage collector, the main reasons we're writing our first number in Java. Okay. Oops. Well, we're going to port it to Rust anyway. And then when we hit a wall, if we do, we'll have to work it out by learning more Rust, which is the whole object of this. Lovely Mono, how are you? All right, next we need blobs of code to implement the evaluation logic for each kind of expression we can parse. We could stuff that code into the syntax tree classes in something like an interpret method. And in fact, we could tell each syntax tree node interpret thyself. This is the Gang of Four's interpreter design pattern. It's a neat pattern, but like I mentioned earlier, it gets messy if we jam all sorts of logic into the tree classes. Supercuber says, naively, cloning will work until you get to environments and closures and stuff. Source, I almost gave up at the closures chapter. Oh no, okay. Well, that'll be an interesting thing, and then maybe we can compare my solution with your solution at that point and figure out what I did or what I will have done. Lovely Mona says, just clone more. Yep. That's the answer to everything in Rust. Just clone everything. And that's actually what we did with this, right? With our parser. Earlier in this session, I created this dupe function for our tokens. So every token now has a dupe function that we can just duplicate everything, which is clone more. It does the trick, but I'm thinking now maybe that wasn't the right answer if we're going to run into issues with environments and closures and stuff. Oh my. Instead, we're going to reuse our groovy visitor pattern. In the previous chapter, we created an AST printer class. It took a syntax tree and recursively traversed it, building up a string, which it ultimately returned. That's almost exactly what a real interpreter does, except instead of concatenating strings, it computes values. So we'll start with a new class, and it's going to be called interpreter. Okay. All right, so it implements expr_visitor object. So in the Rust way to do that, we're going to say use create expr star. We're going to create a pub struct interpreter, and we're going to say impl expr_visitor for interpreter. Right? That's the equivalent. Did I call it expr_visitor? Let's find out. I did. Look at that. Oh, and it needs a type. And it's going to be object. Okay. Oh, and of course it builds. It's not hooked up yet. Not found in the scope. That's easy to fix. Yeah, and now we're missing all our visitor functions. Okay. The class declares that it's a visitor. The return type of the visit methods will be the object, the root class that we use to refer to a lock's value in our Java code. To satisfy the visitor interface, we need to define visit methods. Yep, for each of the 4 expression tree classes our parser produces. We'll start with the simplest. Evaluating literals. The leaves of an expression tree, the atomic bits of syntax that all other expressions are composed of, are literals. Literals are almost values already, but the distinction is important. A literal is a bit of syntax that produces a value. Literal always appears somewhere in the user's source code. Lots of values are produced by computation and don't exist anywhere in the code itself. Those aren't literals. A literal comes from a parser's domain. I'm curious if this is actually a true statement. Can you write code that doesn't have any literals in it at all? Maybe very simple code can. A literal comes from the parser's domain. Values are an interpreter concept, part of the runtime's world. Okay, so we're trying to distinguish between literal and value. In the next chapter, when we implement variables, we'll add identifier expressions, which are also leaf nodes. Okay. Supercuber says the statement is if it's a literal, it's in the source, not if it's source, then it contains a literal. Oh, okay. Yep, you're right. I read it backwards. You're right. So if there's a literal, it's going to be in the source. It doesn't come from outside the source, whereas a value gets generated by an interpreter as a result of interpreting expressions and statements. Got it. Thank you, Supercuber. Okay, so much like we've converted a literal token into a literal syntax tree node in the parser, now we convert a literal tree node into a runtime value. That turns out to be trivial. Oh, Chromos and Drift. Thank you for the follow. POM. So here's visit literal expression. It takes in the expression and returns the value. Okay. And let's just pull up the code here for expr and take a look. So this is what we're going to write. Is there a way to reference this type? Because this needs to be object, right? Is there a way to just say use the type that's up here? I don't know. I don't think you can use self because self is interpreter. Can you say T where T is object and then use T here? Nope. Doesn't like that. Supercuber says doubt it. Okay, I'm gonna go along with the doubt it. That's unfortunate because it'd be nice if I could just say this object is this object. Like this T here is this T. Koopa says you could use an associated type in the trait. And Vengaroth says impl T for where T is object. Oh, okay, like this. And then just put a T here. Object is not a trait. Oh, I would have to make it a trait. T equals object? Is that valid syntax? It is. It is. I've never seen that before. Nope. Invalid type param. So we can't say where T is object because object needs to be a trait. That's unfortunate. Oh well. Maybe something to look for in future Rust. Or maybe it exists and we don't know the syntax for it. Yeah, so we're missing visit binary, visit grouping. That's fine. We'll get there. But right now we're going to just do this. Return expr.value. So this is just okay, expr.value. Right? Is that all that is? Didn't complain. But maybe we just need to add all the others. Vingariath says, if object is not a trait, you don't need to be generic over it. Yeah, so what I'm doing is I'm making this a concrete thing that returns the concrete thing that I'm doing. I just want to be able to say use something to refer to this, so I don't have to put object in each one. Let's pull up that expr again, but I guess there's no way to do that. Which is fine. I'll just put object in each one of these guys. Object, object, and object. And then we can import these guys. You know what I'll do is I'll just say okay for now. Oh, yeah, I can't. Okay, object, nil. And that way at least it'll build. Nope. Oh, I pulled the wrong one. Binary. That's the one I'm missing. Okay, and now it doesn't like this because it found an option. Still didn't like it. Oh, because we're moving the value now. Okay. It's an option object. Should I return a reference? No, I don't want to return a reference to it. Lovely Mona says, what's wrong with writing an object twice? It feels like, situation in programming where you want to have the truth in one location. And if I put object here and then just have this, just refer to that over here, that would be cleaner, because then if I need to change this, I change it in one spot instead of changing it in every spot. I don't see reason to change it. It's a code smell for me. Supercuber says an associated type for the trait does actually seem correct here, by the way. See, for example, iterator traits when they have type output. Oh, I see what you're saying. So you'd say type, object. But we'd have to modify our expr visitor to handle that. And I don't know how to do that. Yeah, and then we just refer to output in each one of these return values. Right, got it. Yeah, right. We'd put type output in the trait. Like here. I can't do it here because this is generated code, right? And get rid of it here and then just put output here, right? Like that. But then if I say type output equals object, can I put output here? Or does it have to be the object? Because what we're returning here is the an object type. All right, I'm gonna not do that for now. because it means changing our generated code. But let me think about it. Maybe I'll play with it offline and see. But meanwhile, we're cloning this, right? We need to clone this unwrapped value. Still doesn't like it. As ref. I never know when to use as ref. Expected enum. Do I have to do it the other way around? Unwrap as ref? Nope. Method not found in object. And of course this is an option which is not yeah, it's saying do that, but it doesn't like that at all. Right, because expected this and found that. And if I put a star there, then it's going to complain about lifetimes. Or moves, sorry. Oh, Supercuber says if we do the object thing, then we can do self colon output here. Yeah, that makes sense. Okay. Koopa says as ref turns an option T into an option ref T. So as ref converts option T into an option ref T. And we don't want an option ref T. We just want to unwrap the whole thing. And if I just do this unwrap, then it's not going to work because it's going to move it again. So do we need to clone it after we unwrap it? And I think I tried that already and it complained about that because there was a move. Oh, we're saying first clone, then unwrap. There we go. Okay, thank you, Supercuber. I'm still, it would be great if we didn't have to clone things and throw them all around. But I think that would require creating, like I was talking about before, creating an object store. And then just referencing the object store. And the object would have, maybe this store would have static lifetime, or at least we could create a locks struct and have the object store inside the lock struct, and then it would be the lifetime of that lock struct, but then we would have to pass that everywhere. All right, well, this works. So I'm going to step back now and say, okay, don't touch this. This is working. So this is probably what happens in Java too, right? When we return this, we're returning an object, but we're actually returning a reference to an object. So maybe we should be pulling in RCs and ref cells and things like that. I don't know if I want to go there because that would be the equivalent code in Rust. It would be using ref cells. Tom Dabrowski, thank you for the follow. Oh, and Vengaria, did I miss you? Did I miss your follow? If I did, I apologize. Thank you for the follow. Supercuber says you'll be pulling them in for closures. Spoilers, dude, spoilers. I think, also he says, I think my visitor got the little expert by value. Okay. All right, well, let's keep going. Let's see if we can get at least, because I only have I have less than a half hour left. Let me see if I can at least get the expression stuff done, and then see if it parses and actually does stuff. Let's see how far we get. Lovely Mona says ban Supercuber. Yeah, no worries. I was just joking. Chromos and Drift says the book uses Java. That's a good question. So what it actually has, and I should go back really quick. Oh, I can't. Let's look at the chapter thing. Oh, and by the way, yeah, definitely check this out. I did buy the book. I'm going through it online, but I did buy the book, a print copy of the book, because this is all good stuff. But we're going through here, the web version of it, and we're at chapter 7 here, tree walk interpreter. This tree walk interpreter is all done in Java. Lovely Mona says Java for the first part and C for the second. Right. So here's part 3, which is all done in C. So I'm going to be going through both of these. But Supercuber was saying earlier, they almost gave up during the not expressions. What did you say? Is doing the environments and closures. So when we get to environments and closures, we might have to lean heavily on chat for help. All right, so here's where we were, right? We eagerly produced the runtime value way back during scanning and stuffed it into the token. The parser took that value and stuck it into the literal tree node. So to evaluate a literal, we simply pull back out. So evaluating parentheses. Oh, call it TwitchBot. Thank you for the bits. Much appreciated. Chromos Undrift said, I've heard it's good. Yeah, it is good. So far, I've been actually learning more Rust than interpreting. But that's only because I've had experience writing interpreters before in other languages. But that's okay. This is all good. This is all good. So the next simplest node to evaluate is grouping, the node you get as a result of using explicit parentheses in an expression. So this just calls evaluate, which we don't have yet. So but we'll put it in here. So we're going to just say, okay, evaluate expr.expression. And we'll probably have to ampersand it, is my guess. But let's see when we get there. A grouping node has a reference to an inner node for the expression contained inside the parentheses. MadFlash says 19 says, is it locks you're working on? Yes, this is locks. Let me throw the link to the book in chat, just in case people want to just click on that. It's also in the description. So a grouping node has a reference to an inner node. To evaluate the grouping expression itself, we recursively evaluate that sub-expression and return it. Some parsers don't define tree nodes for parentheses. Instead, when parsing a parenthesized expression, they simply return the node for the inner expression. We do create a node for parentheses and locks because we'll need it later to correctly handle the left-hand sides of assignment expressions. Okay. So a little bit of foreshadowing here. We rely on the helper method, which simply sends the expression back into the interpreter's visitor implementation. Okay, so here's evaluate. We'll have to put it inside its own. Oh, so we can just say expr here, and it returns an object. Self, I guess. Oh, self evaluate. And it doesn't like that. Oh, this. No, self. So this needs a self. Okay. Oh, right. This is a boxed expression. Or can we just take a reference here and it will automatically unbox? Nope. Yeah, okay, that worked. Expected object, but it found result. Okay, so I guess we can just result. Right? And this can get a question mark on it? Yeah, okay, that works. Who knows if that actually works when we run it, but it compiles. Okay, so there's evaluating unary expressions is next. So we grab the right, we evaluate it. Oh, we're just doing minus for now. Supercuber says if it compiles, it works. Yeah, I wish it were that simple. Okay, so we're gonna do Unary next. So let right is equal to self evaluate expr.write question mark, and then we're gonna say if, I guess, expr operator is token type. I'm just going to do it this way because otherwise Rust is going to complain. Minus that we only have a single match thing in there, and we're going to say return. Oh boy, so minus double right, which will not work. We actually need to convert this into what's the best way to do this? Match right is going to be object num n is going to convert to I guess is going to be okay of object negative n. Oh, no. Anything else is just going to be null. Okay, object nil. And if it's not a negative, then we're going to return null. This says unreachable. But it is very reachable. It is very, very reachable. Supercuber says, I added into num option methods to my object. Oh, yeah, that makes sense. Actually, I was pausing a few times here because I was thinking maybe we can just implement standard ops for these guys. Right? And that way we can just say, if it's a minus, then just say, okay, negative, right. And then have standard ops, the Unary minus implemented. Supercuber says you will need it for binary operators. Okay. Well, let's get this part working, and then we can always add standard ops. And this, I guess, is just going to be, we'll throw an error here. Oh, now we need an interpreter error. Logs error. I'll just use a regular error. Line 0. Unreachable. According to Nystrom. Okay. No thing there. Okay. Oh, we need the token type. Expected. Oh, I have to say just return. And this needs to, excuse me, this needs a toString. And actually I want to clean that up then because I don't want to have to call toString every time we have an error. So that'll be for the next stream. Maybe that'll be the beginning of the next stream is cleaning that up. All right, so 5 warnings, but it's compiling. First, we evaluate the operand expression. Then we apply the Unary operator itself to the result of that. There are 2 different Unary expressions identified by the type of the operator token. Shown here is minus, which negates the result of the subexpression. The subexpression must be a number. Since we don't statically know that in Java, we cast it before performing the operation. Right, so we're doing it slightly different. We're doing it the Rust way here. This typecast happens at runtime when the minus is evaluated. That's the core of what makes the language dynamically typed right there. You're probably wondering what happens if the cast fails. Fear not, we'll get to that soon. Yeah. You can start to see how evaluation recursively traverses the tree. We can't evaluate the Unary operator itself until we evaluate its operand subexpression. Right, that's what's happening up here. Right, we evaluate the subexpression and then apply the Unary minus. That means our interpreter is doing a post-order traversal. Each node evaluates its children before doing its own work. The other unary operator is logical not. In case bang is truthy. Okay. So, okay, so now here's where we're going to do the match. Match, expert operator, token type. And this will be token type minus, which is going to get this thing here. Cargo format, come to my help. There we go. This is going to get our error. Oh, there it is. And we can delete all those because I was going nuts with that. Okay, and that closes that. That closes that. That should format. Yep. Okay, good. So now we can add a token type bang. And then we're going to return, okay, self is truthy. Oh, not self is truthy. Oh, not self is truthy. Which means we're going to say if self is truthy of right, then we're going to return, okay, object false, because we're nodding it, else. Okay, object true. And cargo format, thank you. And we just need to write is truthy, which is right here. And this implementation is simple, but what's this truthy thing about? We need to make a little side trip on one of the great questions of Western philosophy, what is truth? Timophane, thank you for the follow. Okay, truthiness and falsiness. Inside the world of locks, we need to decide what happens when you use something other than true or false in a logic operation like bang or any other place where a Boolean is expected. We could just say it's an error because we don't roll with implicit conversions. And that's the way Rust works, right? I mean, you have to have a bool in here. But most dynamically typed languages aren't that. I don't know how to pronounce that word. Ascetic. Okay, we'll go with ascetic. Instead, they take the universe of values of all types and partition them into two sets, one of which they define to be true or truthful, or my favorite, truthy, and the rest which are false or falsy. This partitioning is somewhat arbitrary and gets weird in a few languages. In JavaScript, strings are truthy, but empty strings are not. Arrays are truthy, but empty arrays are also truthy. The number 0 is falsy, but the string 0 is truthy. Yeah, there's a whole JavaScript Watt video. That's pretty funny. Oh, it comes from Destroy All Software. Yeah, so check this out if you haven't already. I'll put that in chat. This is pretty good. This is, oh wow, it's 10 years old now, but it's still funny. In Python, empty strings are falsy, like in JavaScript, but in other empty sequences are falsy too. In PHP, both the number 0 and the string 0 are falsy. Most other non-empty strings are truthy. You get all that? There's going to be a test later. Locks follows Ruby's simple rule. False and nil are falsy, and everything else is truthy. Okay, we implement that like so. So that comes down here. And we're going to pass in an object, and I'm going to take in reference to an object to avoid passing the whole object in or copying it or whatever. And it's just going to return a bool if object is null. So object is object nil. Return false. If object is instance of a Boolean, return Boolean object. If matches, bang. Oh, that should be a comma. What am I doing? Object. And it's going to be object false, or object true. That's how we're going to do the instance, but now we have to destructure it. Oh, there's got to be a simpler way to do this. Yeah, and I think there is, right? If I say match object, object false, false, no, true. Yep, object true is true, and everything else is true. And by writing that, we can see how we can simplify that a lot, right? Because we can say here, we can just pull this in, or that is false, and that matches those, and this can just be everything else, which means we can say if matches bang object nil or false, false, else true, right? Is that the simplification of it? So if we have null, we return false. If we have a false, we return false. And everything else is true. Supercuber says, I had an object Boolean bool variant. Oh, I see what you're saying. That makes sense, right? So instead of this, we say bool, bool, right? And then just have that value in there. Okay, let me think about that. Unfortunately, I'm just about out of time, so I'm not going to make that change now, but that might make sense. Especially given this, we could just, if we had that, we could just say, okay, object bool self is truthy, right, and convert that to one line of code. And Supercuber is pointing out that we could just reduce this to one line of code by putting a bang in front of here. And an ampersand there. That's great. I like this syntax. Bang matches bang. It's almost like a Spanish exclamation. Yeah. It is chef's kiss. I'll give you the chef's kiss. But the question is, how readable is it, right? The other version was you know, if you look at it, you can see what it's doing. Here you have to, but we can just put a comment here. Anything that is not nil or false is true. Okay, so that helps. Because otherwise you have to look at it and say, okay, it matches this, but it doesn't match it, so therefore, okay, right? Whereas the other version, you could actually read it almost like English. But we'll throw the comment in there, and we should be good to go. Okay, and then we have binary operators. On to the last expression tree class, binary operators. There's a handful of them, and we'll start with the arithmetic ones. Did you notice we pinned down a subtle corner of the language semantics here? In binary expression, we evaluate the operands in left to right order. If those operands have side effects, that choice is user visible, so this isn't simply an implementation detail. If we want our two interpreters to be consistent, hint we do, we need to make sure clocks, or clocks, does the same thing. So yeah, that was that second version that we're going to get to much later. The bytecode version of this. So I'm going to save binary expers for the next stream. We'll do that tomorrow. Because like I said, I think I want to do standard ops to do it, so we don't have to do all this instance of crap. And so we need to think about the right way to go about doing that, and I don't have the time today, unfortunately. I have 4 minutes left. What are the warnings now? Because we're using nil. Oh, we're still not using synchronize, right? And binary expert isn't being called, so let's just underscore that one. And now our only warning is synchronize. Okay, git status, git add source, git commit -m section partway through section 7.2, writing an interpreter. And let's push this up. Where is it? Do I not have it public? There it is. I just need to put it on my thing there. Okay. And there we go. Commits. All right, so we're good. Chromosome drift pasted in an upside down question mark. Yep. I wish I knew how to type that because I'd respond that way. Okay. So tomorrow we're going to start with, oops, no, not that, this. Evaluating binary operators. And there we go. Chromosome drift says, for me, it's alt question mark. Yeah, I don't have that option though. Oh, wait a minute. I do. There you go. I'm on a Mac, so I hold down Option Shift and then the question mark / key on my keyboard. Look at that. Learn something new every day. Will that work over here? Yes, it will. Very cool. All right. Anyway, thank you everyone for hanging out with me. I hope you enjoyed it. I had a great time with this, and hope to learn a little bit more tomorrow with binary operators, and hope to see you there. All right, take care.